Hi, in this video, we're going to talk about universal quantum computation. So let's talk about initially the universality of single qubit quantum computation. So just say, let's say we are in just the domain of single qubit gates. So single qubit gates. And let's say we have a gate set G, which is just a discrete set. So it consists of gates G1, G2, and Gn. So in this context, what does universality mean? It means that if I have a single qubit unitary U, then I can approximate it uh, to arbitrary accuracy by using gates only in the set G. That means U is nearly equal to GI1, GI2, GIL. And of course, as L increases, the accuracy to the gate U also increases. Now, what does this nearly equal to mean? It means that the distance between U and this gate set can be made arbitrarily small. In other words, I can say that the norm of U minus GI1 GIL, let me just write acting on some vector V and max over V, this can be made as smaller. So given epsilon greater than 0, the distance between the target unitary U and the gate sets G1, GI1, GIL can be made smaller than epsilon for L large enough. So for as you increase the number of gates, the approximation gets closer and closer. All right. So, talking about single qubit gates, last time I had talked about the block sphere picture. So we had the picture of the block sphere. So we had the block sphere, and I said last time that a quantum gate is a rotation about some angle about an axis of the block sphere. So let's say this is n, and this is determined, but the axis is determined by the vector n, and we have another axis m. So if I am able to generate an arbitrary rotation about this vector n, so let me call that Rn of alpha. And then I'm also able to get a rotation about this axis m, where m and n are non-parallel, right? So if I'm able to get these alphas and betas, but the caveat is that alpha and beta have to be irrational multiples of 2 pi. Multiple of 2 pi. If these two conditions are met, that is, m and n are non-parallel and alpha and beta are irrational multiples of 2 pi, then I can generate an arbitrary rotation about any other axis, right? And uh, why do we need this irrationality? So if I look at the view from above, so let's say I have this view. So now this is a circle and I'm able to generate a rotation alpha. And if alpha is an irrational multiple, then I should be able to sort of go around the circle and come arbitrarily close to any angle, let's say theta. So I can make several rotations to come as close as possible to theta. If that wouldn't be possible if alpha or beta were rational. So that is for single qubit. And now let's move on to uh, to an arbitrary n qubit unitary. So once you have a universal set of single qubit unitaries and an entangling gate such as a C0 gate. So for so universality. So what does universality mean for n qubit universal set for n qubit unitaries? So it turns out that if I have the following gate set, so this G universal, so the set G, which is the universal set for single qubit, and an entangling gate such as the C0 gate. These gates, these set of gates are universal for n qubit unitaries, which means I can generate any n qubit unitary using gates from this set. Now, important question is how many gates will we need to accomplish this universality? It turns out that most unitaries, most n qubit unitaries require an exponential number of gates. So U is will require nearly order of 4 to the power n gates. So the picture is not so good for an arbitrary unitary, although there are several unitaries which can be approximated by polynomial number of gates. And as we go into quantum algorithms, one of the measures of quantum, the success of quantum computing will be to develop efficient unitaries, right? And it turns out that even in the classical case, if I have a function, so classically, if I have a function throwing from 0, 1 to 0, and then we know that gates such as the NAND gates are universal for classical computation. But in general, it will require most functions like this will require 2 to the power n over n classical gates. Okay, so and finally, uh, let's talk about the specific universal set of gates that can be used for universal quantum computation. It turns out that the for single qubit universal quantum computation, so single qubit universal set, there are several universal sets, but one of the famous ones is this set H and T gate. So where H is this 1 over square root of 2, 1, 1, 1 minus 1, and T is 1, 0, 0 e to the I pi by 4. Right. So this set is universal for single qubit quantum computation. And to show this, the proof is just working your way around the block sphere and showing that using this set, you can generate uh, two non-parallel rotations about the block sphere, and the angles are irrational multiples of 2 pi. So then, of course, the G prime is equal to H T C naught is a universal set for n qubit quantum computation. So let's take a few examples of what may not be a universal set. So examples of gate sets that are not universal. So the first is the C naught gate. Now the C naught gate takes the 0 to 0 0 0 1 to 0 1 1 0 to 1 1 and 1 1 to 1 0. So notice that it doesn't create any superpositions. So the reason that the C naught gate is not a universal set is because it doesn't create any no superpositions. So does not create superpositions, no superpositions. Then what about other gate sets? So the second gate set that we'll talk about is the Hadamard gate. So the Hadamard gate is just a single qubit gate. It does create superpositions. It takes get 0 to 0 plus get 1 over square root of 2 and get 1 to 0 minus 1 over square root of 2. But just this single qubit gate cannot create any entanglement. So therefore, this does not create no entanglement. And then if I, let's say, take some other set, such as, um, let's take another set, such as Hadamard and then S and let's take a different one. Let's take C naught and H. What's so now we have create superpositions, right? This gate set can create superpositions, can create entanglement, but is still not a universal set. So the reason for that is that it just creates it, so it takes generates real unitaries, but no complex unitaries are generated. So no complex unitaries, right? So it is not universal. And then let's take one more. Let's take H C naught and the S gate, where the S gate is this 100 I, right? So it turns out that due to a theorem in error correction called the Gottesman-Nil theorem, so this is Gottesman-Nil theorem, this gate set can be simulated efficiently classically. So there is again, this is not a universal set. So this theorem we will learn when we do error correction. But regardless, this gate set is not a universal set. And finally, the one which is a universal set is this gate H, this set of gates. So H, T, and C naught. So this is 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 universal. All right. And so one final topic about what is known as the Solovay-Kitaev theorem. So I initially mentioned that if I want to suppose I have a universal set, then one can approximate any arbitrary unitary to within epsilon. But how does the number of gates scale with epsilon? So suppose, so this is the Solovay-Kitaev theorem, Solovay-Kitaev theorem. So suppose I have a universal set G. So let G be a universal set. And one of the conditions of the Solovay-Kitaev theorem is that if a gate G is in this set, then G inverse is also in the set that contains. So that contains inverses. And suppose U is an arbitrary unitary. U is an arbitrary unitary. Then to approximate U to within epsilon greater than 0 requires order of log of 1 over epsilon gates. So there is some constant C over here, gates in G. So the scaling is reasonable, manageable in terms of epsilon. So in general, if I want to approximate, let's say, an arbitrary n qubit unitary, so it will require, so n qubit unitary will require approximately order of 4n into log of C1 over epsilon to within epsilon accuracy.